Hello everyone and welcome to our event. Thank you for joining us to hear about meeting our Sustainable Development Goals through an integrated carbon management approach. So today we want to talk about achieving our sustainable goals and pathways to 1.5 degrees require large-scale reduction and negative CO2 emissions, which requires a flexible and coordinated approach. So the aim of our event is to inform you on the need for a portfolio of emission reduction and saving technologies to meet our climate targets, and to share some of the complementary options we can use to reduce and reverse our CO2 emissions. These options need to be rapidly implemented in order to achieve net zero by 2050. So the IPCC 1.5 degrees special report shows we need to achieve net zero emissions by 2050 to limit our global average temperature to 1.5 degrees, including up to 300 gigatons of CO2 from primary energy production removed from the atmosphere and stored. So we're here today to talk to you about nature-based solutions such as peatland rewetting and CO2 capture, utilisation and storage, which are essential in tackling the climate challenge. Natural CO2 sinks, industrial CO2 capture and secure geological storage, and low-carbon building materials all have an essential role to play in meeting our climate targets. Utilisation can add value to help us realise the economic, environmental and societal potential of CO2 removal. So the key thing is we can't afford to ignore any of the tools available, and we need to consider what is ready now and what will be available in the future to help us meet our climate targets. Governance needs to support an integrated approach, but implementation will need to be adapted to match the opportunities presented by different situations and locations. How we act now will determine if we succeed in meeting the climate challenge. So we've got a great lineup of speakers, and we will also have a question and answer session. So I hope you can see the Slido Q&A link, the little pink symbol under the session description. And I encourage you to post your questions and we will try to answer as many as we can. So as I said, we've got a great lineup of speakers today. And first I'm going to go swiftly on to introduce Eva Halland, who is Project Director for CCS and CO2 offshore storage in Norway for the Norwegian Petroleum Directorate. So please can we move on to Eva's presentation? Thank you. Eva, the floor is yours.
And thank you. Thank you for the introduction, Kerry, and also for the invitation to talk about a topic I'm passionate about and a topic that is extremely important for achieving this set of climate goals: carbon capture and carbon dioxide capture and storage, called CCS. Next slide, please. Over its years of development, CCS has faced questions about its technical feasibility and safety. In Norway, CO2 has been injected and stored for 25 years under the seabed, and more than 26 million tons of CO2 has been permanently stored. The CO2 is stored deep beneath the seabed into saline aquifers, which is porous geological formations containing water and which have up to hundreds of meters of thick shale layers sealing the CO2 in the reservoirs. The world's first offshore CO2 storage project was the Sleipner CCS project, as you see on the left side of the screen. This is storing around 1 million tons of CO2 yearly from 1996. Today, this storage site is a hub in the area, with 3 hydrocarbon fields storing the captured CO2 into the same storage site. And from 2008, CO2 captured from the Snøhvit hydrocarbon field up north in the Barents Sea has been injected and permanently stored nearly 3,000 meters under the seabed. That's the figure on the right side. It's a subsea development. So the development and operation of the CO2 management projects at Sleipner and Snøhvit have for several decades demonstrated safe storage of CO2 in geological formations under the seabed. Safe storage is supported by monitoring programs that new projects can benefit from. And the data from these projects are shared with research communities and other stakeholders. Next slide. In 2014, the Norwegian Petroleum Directorate launched the Norwegian CO2 Storage Atlas, and the same year the regulations for CO2 transport and storage were published. That's as an implementation of the European Union's CCS directive. The aim of this atlas was to find a good overview of where we can store CO2 offshore Norway and how much CO2 can be stored. So the Norwegian Petroleum Directorate has access to all data collected from the petroleum industry and has a national management responsibility for this data. So our data, overviews and analysis make up an important and large fact basis from more than 50 years of oil and gas activities on the Norwegian continental shelf and 25 years of CO2 storage. So depending on their specific geological properties, several types of geological formations can be used to store CO2. In the North Sea basin, the greatest potential capacity for CO2 storage will be in deep saline, water-saturated formations in depleted oil and gas field or fields with ceased production. As you see on the right slide, there's a lot of huge saline aquifers mapped out in the North Sea basin. So next slide, please. This knowledge and experience also resulted in our government gaining confidence to begin considering a possibility of developing a full-scale CO2 capture, transport and storage project. This is the Longshape demonstration project. This project reflects the Norwegian government's ambition to develop a full-scale CCS value chain in Norway by 2024, demonstrating the potential of this decarbonization approach to Europe and the world. Longshape includes capturing CO2, as you see on the map here, from industrial sources in the Oslofjord region, and that's CO2 from cement production and waste to energy, and shipping liquid CO2 from these industrial capture sites to an onshore terminal on the Norwegian west coast. From there, the liquefied CO2 will be transported by pipeline to an offshore storage location, subsea in the North Sea, for permanent storage. This will be the first ever cross-border open source CO2 transport and storage infrastructure network and offers companies across Europe the opportunity to store the CO2 safely and permanently underground. Phase 1 of this project will be completed in mid-2024 with a capacity of up to 1.5 million tons of CO2 per year. So with this Longship project, we hope to accelerate decarbonization, develop a full-scale CCS value chain, contribute to developing technology for capture, transport, and permanent storage of CO2, facilitate cost-effective solutions for full-scale CO2 management, demonstrate that CO2 management are safe and possible. CCS here can also enable negative emissions as part of large-scale deployment. And this is really important. And it can facilitate learning and cost reduction for other projects and future projects, facilitate the business development, and demonstrating the potential for this decarbonization approach to Europe and the world. Next slide, please. So storage site, safe storage site for CO2 are available with large capacity. Around 1 to 1.3 gigaton with the capacity are more or less to be ready to be developed, and around 800 gigaton to be explored further in the geological formations from around 700 meters down to 3,000 meters below the seabed in the offshore Norway part. Next, please. So following the government's decision on the Longshape project, we began to see an increased interest in developing CCS value chains. So the next phase will be to start creating a sustainable future for CCS. The Ministry of Petroleum and Energy announced 2 new areas for CO2 storage with an application deadline of December 9 this year. And we see this also happens several places in the North Sea basin. One area will be of the announced area is in the Barents Sea, shown on the left slide, and one in the area in east of the Troll field and east of the Longship license in the North Sea. And we really look forward to seeing how big this interest will be for the new areas. So the next, please. So just to sum up, we have the knowledge for safe storage of CO2. Through 50 years of the oil and gas industry on the Norwegian continental shelf, we have mapped, collected, and interpreted geodata. We have the instruments. The information from the oil industry gives us a good overview of the reservoirs. We set requirements and solid regulations in place. We have the experience. CO2 has been injected on the Norwegian shelf for more than 25 years, and which we monitor closely. We have a huge potential. Our mapping and evaluation show that there is capacity to store as much as 80 billion tons of CO2 offshore Norway. And if we are looking at the whole North Sea basin, the capacity is really big. And it's ready now. CCS is a key part of meeting our climate targets and decarbonate the industry. And the knowledge and technology is ready now. So next, please. Thank you for the attention, and I'm happy to answer any questions you will have afterwards. Thank you.
Thank you very much, Eva. Fantastic to hear that CCS is moving forward so positively in Norway, and that we have real projects and real CO2 in the ground as part of tackling the climate challenge. So thank you very much for this. And we're going to move on to our next speaker, who will talk to us about how utilisation can add the value. So our next speaker is Barbara, who is Research Group Lead for CO2 Utilisation Strategies and Society at the Institute for Advanced Sustainability Studies. Barbara, the floor is yours.
Thank you. Thank you very much, Carrie. Thank you for introducing me. And I'm very glad to be here today and have the opportunity to introduce you to the concept of CO2 utilization in the next 5 minutes. Carbon capture and utilization, in short CCU, denominates technologies and processes that utilize carbon dioxide from different sources, either directly or after a chemical conversion as part of a carbon compound in materials or energy carriers. Alternative denominations are, for example, CDU, carbon dioxide utilization, CDR, carbon dioxide removal, or CCUS, combining CCU and CCS. Next slide, please. A CCU process comprises 3 phases. The first is the capture phase, indicating where the CO2 for utilization stems from, like capture from industrial point sources, like biological uptake, or like capturing it directly from the air. You can see that in the upper part of this circle. The second phase is the utilization phase. Here, the CO2 is either used directly or after a chemical conversion in carbon compounds, resulting in products like, for example, liquid energy carriers, like solvents or different sorts of plastics. products resulting from mineralization processes, which you can see on the bottom of the circle, have the additional advantage of permanently storing the CO2. This is, for example, aggregates or concrete. The third phase is the end-of-life phase, indicating different options of product disposal and current gaps in the desired industrial carbon cycle. The red arrows indicate companies that have CCU products on the market already, making CO2 utilization a reality in many sectors already today. Next slide, please. Estimates on the potential of how much CO2 can actually be used annually in 2030 range from 5 to 7 gigatons, with the biggest potential currently being seen in the building industry with aggregates and concrete, where, as I said, additional advantage is that the CO2 can be stored long term. In this context, it's also important to notice that CO2 utilized is not equivalent to CO2 reduced, because additional process emissions may occur and in comparison to the conventional benchmark product. Next slide, please. CCU technologies span diverse industrial sectors, and their implementation can have many different interactions with societal change processes, such as, for example, energy transitions, industrial modernization and decarbonization, or also the development of decentralized energy supply structures. At the same time, undesirable path dependencies must be avoided in future research processes, but also in upscaling and implementing CCU in reality. In order to ensure development and implementation in line with the benefits of societies, it's useful to assess the compatibility of CCU with the Sustainable Development Goals. Next slide, please. 5 out of 7 SDGs can be fostered with the implementation of CCU technologies. SDG 7, affordable and clean energy for all, can be supported by Power-to-X technologies, utilizing CO2 and hydrogen to produce energy carriers, which provide energy storage options. New decentralized energy solutions may become possible, probably in connection with direct air capture in areas with lots of solar energy potential. CCU promotes sustainable economic growth, SDG 8, through the conservation of resources by substituting fossil raw materials. As a driver of sustainable innovation, CCU can contribute to industrial innovation and infrastructure as an SDG 9, also by retrofitting industrial plants with capture technologies and thus making them more sustainable. Responsible consumption and production, as in SDG 12, can be fostered by CCU as a potential pathway for more sustainable production processes. Also, the more efficient use of natural resources and the creation of an industrial carbon cycle adds to this. And finally, CCU has the potential to contribute to SDG 13, combating climate change. Overall, CCU provides different benefits for societies in the context of economic innovation and of achieving energy and climate targets. Their implementation, though, needs to be carefully monitored to avoid lock-in effects and path dependencies, for example, with undesirable energy production or outdated industrial facilities. Since CCU is not a business case yet, it needs policy support now and will continue to do so in the foreseeable future. For a successful, sustainable, and forward-looking implementation of CCU technologies, decision makers in politics and funding bodies are therefore asked to ensure the necessary conformity with sustainability goals. Taken together with CCS and other carbon management measures, the emission reduction potential is significant. Thanks for listening.
Thank you very much, Barbara, for an introduction to share with us how CO2 storage and utilisation can form a key part of meeting Sustainable Development Goals. Thank you very much for this insight. And we're now going to hear from one specific utilisation from Claude. So Claude is Cement Director at the Global Cement and Concrete Association. Claude, the floor is yours.
Thank you very much, Cherry, and good day, everyone. I would like first to frame this utilization in the context of our concrete future. So I'm speaking on behalf of the GCCA, the Global Cement and Concrete Association, and we have last month released our concrete future, which is our roadmap to achieve net zero emission by 2050. We can move on the next slide, please. So it shows the road to net zero. I really want to emphasize concrete is an essential and sustainable building material that's going to be essential to build the world of tomorrow and also to meet the challenges of the future generation. Concrete is needed for renewable energy, schools, hospitals, sustainable buildings, and with the growing population, we really need concrete. But we also need to get our emission to zero. And this shows the pathway to net zero. So we will build on the reduction that we have already achieved over the last 30 years. So that was 20% reduction. In the decade to come, we will achieve a further 20% reduction. And then we will move to net zero from 2030 to 2050. We have moved a bit too fast to the next slide, so please stay on this one a little bit longer, please. And really, so this decade is the decade to make it happen. And now we can move on the next slide. And I really want to link to the presentation of the first speaker. I know I will speak about utilization in concrete, but you see here how important CCUS is to this net zero pathway. So 36% of the emission reduction will come from CCUS. So the technology is really essential. I was really happy to see the last slide of Eva, because we will really need it as the sector. But you also see next to this big purple box, there is a small blue box. 6% of the reduction comes from what we call recarbonation, and we can move on the next slide, please, because that's really the one I now want to spend time on. So this is really what we call, or what actually now IPCC has recognized in its 6th assessment report, and this is what they call the thing associated with cement carbonation. So it was just mentioned earlier as well, cement production has 2 types of emission, fuel emission and process emission. Process emission come from the decarbonization of the limestone, which is our raw material. So we have a lot of CO2 that is not fuel related, that is actually process related. And this reaction that takes a lot of energy to go in one direction actually naturally happens the other way around. Carbonation is something that structural engineers have tried to prevent for many, many years, but still very tiny layer, surface layer of concrete recarbonates. And in fact, over its lifetime, concrete reabsorbs CO2. And this is this 6% emission reduction. Now, we can obviously push this further. First of all, and this is where now we really come in the CCU field, where first of all, we can, at the end of life of concrete, when buildings are demolished, then the concrete is crushed, and then we can go further with the carbonation of the concrete and then use more CO2 to produce what we call recycled aggregates. It is then used to make new concrete. So that's the carbonation of recycled concrete, or the manufacture of artificial aggregate. You may have spotted one slide earlier. We saw carbon 8 as one the option that was presented by Barbara on her big wheel. So that's another application. And then another CCU option is where the concrete is, instead of being cured with water, is actually cured with CO2. And this is what we call, you have project or products like Solidia, you may have heard about. This is really then a different type of clinker cement. And then it hardens when CO2 is injected. So there are many ways, in fact, concrete can use the CO2, and we have this application of use. And what I really want to emphasize here is that this is a CCU option that actually delivers permanent or very long-term storage, or at least equal to geological storage. So the CO2 is not re-emitted later. The CO2 is really embedded in the final building material, in the final product. So that's very important to understand that it's a different CCU option than the other CCU option from that perspective. If we move on the next slide, delivering this is something that we won't be able to do alone. So we have a big call. I think this is where we are at COP at the end. We have a big call on policymakers to support with policies. Obviously, we need policies for CCUS. We need to make low carbon cement manufacturing investable. We need to have the demand for low carbon concrete products stimulated. And then we need infrastructure needed for a circular and net zero manufacturing environment. And in fact, that infrastructure issue is really, really key in the context of CCUS, but also key in creating this circular economy that, for example, we will need to carbonate recycled concretes. We need to make sure that construction and demolition waste reach the right place, and that the CO2 that it has been captured can also be transported. So we have this access to transport, infrastructure, and then also we need a fair recognition of all CCU options with adapted carbon accounting. So thank you very much. I think we have time for a discussion later, and I hope I made it in 5 minutes, Ari.
Thank you very much, Claude, and I love your rallying cry. This is the decade to make it happen. So I very much appreciate you talking to us about what are the utilisation options for long-term storage of CO2. So we're not just talking about CO2 that gets re-emitted, we're talking about trapping it permanently in concrete. So thank you very much. And I will move on to our next speaker, who is Franziska from the Institute of Botany and Landscape Ecology and a member of the Greifswald Meyer Centre. So Franziska, the floor is yours.
Thank you very much. I think something happened to my slides. They do not look as they used to look, but we will manage. I will talk about nature-based solutions and with a particular attention to peatland restoration. Next slide, please. Ecosystems have the potential for large additional climate mitigation by combining enhanced sinks with reduced emissions. So here you see recent data from the Global Carbon Project, the anthropogenic fluxes for the period 2010 to 2019, averaged over this period in gigaton CO2 per year. You see, of course, the large fossil CO2 source on the left-hand side. You see another smaller source of land use change in orange, but you see also the biosphere sink. And so this is what I've just said. So you may reduce emissions, you may enhance emissions by better managing ecosystems. And then on the right-hand side, you have the ocean, which of course also plays an important role. Next slide, please. So what do we mean by nature-based solutions, by working with nature? This includes all activities where we actually work with nature to address societal challenges. And the climate crisis is a particularly urgent societal challenge. So here in the context of the climate conference, we talk about natural climate solutions, NCS. They include conservation, restoration, and improved land management actions that increase carbon storage and or avoid greenhouse gas emissions across global forests, wetlands, grasslands, and agricultural lands. They can provide over 1/3 of the cost-effective climate mitigation needed between now and 2030, so in this decade, to stabilize warming to below 2 degrees. We need aggressive fossil fuel emission reductions, so nature-based solutions should not prevent us from doing so. They offer, in addition, a powerful set of options for nations to deliver on the Paris Climate Agreement, and they can help improving soil productivity, cleaning our air and water, and maintaining biodiversity. Next slide, please. So what is then the dimension, the scale of the different natural climate solutions? On this chart, we see on top the forests and their climate mitigation potential in 2030 in petagram or gigaton CO2 equivalents per year. And you see and you know that forests play an important role, in particular reforestation and avoiding forest conversion. You see also in the middle part agriculture and grasslands and a wide range of options related to land management. And then on the bottom, wetlands. And here you see peat restoration, avoided peat impacts, and with quite a substantial amount of climate mitigation potential. And I will focus now on peatlands because they are often overlooked so far. Next slide, please. So what is a peatland? On the picture, you see, to our knowledge, the oldest drawing of a peatland in Europe. A peatland is an area with a naturally accumulated layer of peat at the surface. So peatlands have proven, not for 20 or 30 years, but for centuries and for millennia, that they accumulate carbon and that they are able to store it and to keep it in the ground. And you see the peat column on the right side to the text. Peat is sedimentarily accumulated material with more than 30% dead organic matter, dead plants basically. So peat formation is carbon sequestration and storage. This peat layer is preserved under wet conditions, but it oxidizes to CO2 under drain conditions. In IPCC terms, we usually talk about organic soils. Most organic soils are peatlands. Next slide, please. So this is just a preview of the new global peatland map, which will be actually launched next week here in Glasgow at the COP26. But just to give you an impression of the distribution of peatland, we have a lot of peatlands in the Northern Hemisphere. We have a tropical belt of peatlands, and we have some peatlands on the Southern Hemisphere, but we lack land basically. So we have less peatlands on the Southern Hemisphere. Next slide, please. What is very important, peatlands can be either a sink or a source of carbon. And here the two charts indicate the good condition. In gray is the sink situation, and then in red, the source situation. They show the annual greenhouse gas flux from anthropogenic peat loss and peat formation in the period 1850 to 2100, without and with peatland restoration. So on the left-hand side, it is without peatland restoration, and on the right-hand side with restoration. And you see a kind of turning point was around 1916. At this point in time, the global peatland biome turned from a net sink into a net source of soil-derived greenhouse gases due to drainage and peat oxidation. Annual back conversion of most of the drained area would render peatlands greenhouse gas neutral, whereas emissions from peatlands may comprise between 12 and 40% of the greenhouse gas emission budget for keeping global warming below 1.5 to 2 degrees without restoration. So it's a big risk if they continue to be drained, but also big potential. Next slide, please. Of course, the importance of peatland emissions differs a lot between countries. And here, this shows peatland emissions as % of national fossil fuel and cement emissions. And you see several countries in Africa, for example, in Southeast Asia, but also in Europe, where more than 50% of the national fossil fuel and cement emissions come from peatland, from drained peatlands. Next slide, please. The peatland greenhouse gas hotspots in terms of emissions are Southeast Asia, but also Europe. And here on the map, we have the degree of peatland degradation for all the European countries. In many countries, it is more than 50%, and in a few countries, including my own country, Germany, it's even more than 90%. Drained peatlands in Europe constitute 5% of the total annual greenhouse gas emissions, more than 200 megatons of CO2 equivalents per year. What is very interesting, most of the peatlands have been drained for agriculture, and the right chart shows in the center circle the proportion of peatlands in total agricultural land. On EU scale, it's only 3%. But 25% of all emissions related to agriculture come from drained peatlands. And in a couple of countries, you see that the outer circle is even much, much larger in red. So it's a disproportionately large and very small area. So it is also a big chance actually to change land management to reduce emissions. Next slide, please. Revetting of peatlands involves methane, and we can discuss about the importance, of course. What I would like to show here is that in any case, you have to choose either between methane emissions from the revetted peatland for a certain period of time, or between the continued CO2 emissions. And if you convert all of the gas fluxes to radiative forcing, and if you look at different scenarios, you see that the blue scenario gives the least warming effect. And this is a revetting scenario where peatlands are rapidly revetted, promptly revetted. Next slide, please. Here we have calculated or demonstrated an emission reduction pathway for German peatlands, 1.8 million hectares. On the left-hand side, you see the condition today. Most of the peatlands are still dry. I said that more than 90% have been drained. For the next 3 decades, we need to come to a pathway towards wet conditions in peatlands. So the Paris Agreement actually implies that all peatlands are wet or revetted. And only with such an emission trajectory, we would get in line with what the IPCC 1.5 degree report proposes, that we come to net zero CO2 emissions by 2050. Next slide, please. Such a pathway would imply a fundamental change of agriculture on peatlands. On the left-hand side, you see a typical conventional agriculture on drained organic soils, on drained peatlands. This involves a sneaking but steadily loss of the peat layer. The IPCC emission factors for drained organic soils in the temperate region are between 30 and 40 tons of CO2 per hectare and year. With paludiculture on the right-hand side, which means wet agriculture or forestry on revetted peatlands, the peat layer would be preserved and you would still harvest biomass because the above ground biomass is not needed for peat formation. Emissions are much lower, with between 0 and 8 tons CO2 equivalents per hectare and year. Next slide, please. To develop paludiculture, it is important to develop new value chains for construction and insulation material, fiber for paper, bioenergy, biorefinery, or potting substrates from peatland plant biomass. Such products have already been demonstrated, and they are 3- to 4-fold climate protective. So first, they reduce soil-borne emissions. They may replace fossil resources. You can have carbon sequestration and storage then in long-term life products. And in wet peatland, additional carbon sequestration through new peat formation may occur. Next slide, please. Last but not least, wet peatlands help achieving the Sustainable Development Goals. We have seen them before today. They are very important for our future, and you can link wet peatlands to all of the 17 Sustainable Development Goals. So they all have a positive influence. And in particular for wet peatlands, it is clean water, water purification, denitrification, filtering out pollutants, but also responsible production, climate action, of course, as I mentioned before, and wet peatlands are also very important for maintaining and preserving biodiversity. Next slide. So I would like to thank you for your attention and also invite you to the Peatland Pavilion. So for the first time ever at the climate conference, we have for the entire 2 weeks a pavilion dedicated to peatlands in Glasgow. So you're welcome to join in. Thank you very much.
Thank you very much, Franziska. And thank you for sharing with us the role for nature-based solutions and highlighting that when we talk about achieving 1.5 degrees, we have to understand the role that everything has to play, including that all peatlands would need to be re-wetted to help us meet our Paris Agreement targets. I think that's something really important to take away from this presentation. So I'm going to hand over to Paul Frisvold now, who is going to moderate the Q&A, but first he's going to talk to us about the key messages from our event so far. So Paul is an EU Climate Pact Ambassador and an EU advisor to SINTEF Research Organisation. So Paul, the floor is yours.
Thank you very much, Siri, and good evening, everybody. I hope you can hear me well, because I'm actually sitting at the COP26 venue in Glasgow, where there is a lot of people, and therefore a lot of noise. So I hope that I speak loud enough for you to hear. First of all, I want to thank the our friends who gave their presentations today. There was a lot of interesting information. I've been working in the CCS scene for a long time, but I'm always impressed by our capacity to compress a lot of information. But I think, as Kerry said, there are some key messages. I was actually going to throw the ball back to our presenters today and do the summing up afterwards. But as you can see, what we heard is that this is achievable, this is safe, it can be done. We need the infrastructure. We have the long-term capacity. We need a adapted accounting system. And last but not least, fascinating last presentation by Franziska on the nature-based solution and what it has to offer. So if I then use the occasion of the time we have left to convey some of the questions that came in during the presentations. And the questions are basically in two camps. And I think we have to address the first one very quickly, is about the safety aspect. So people want to know, is this safe? Can it leak? For how long does it stay there? And the other one is the cost element. What will make this become commercially viable so the industry can take up this technology and make it widespread and allow it to reduce the emissions that we so badly need. So why don't I start with you, Eva Holland, because you gave us a lot of figures. And I have 3 questions for you. And this is what our viewers are concerned about. First, about capacity, because you mentioned some figures. And the figures seem huge, but could you say something about the capacity to store versus the capacity to remove? How much of that carbon we need to take away from the atmosphere can you or we actually store? That's the first question. And then obviously, is there a time limit? People are concerned with, will it seep out over time? When you do geological storage, how long can it stay down there? And is there a risk for leakage in the geological formations? And finally, Eva, the third question I have for you, a lot of questions for you, but in Norway, the experience is very much petroleum, oil and gas led. And we know we need to do this on a wide scale, including industry, waste sector, and so forth. And, shouldn't the storage thing be actually handled like we handle waste? Publicly appointed entities that do this on a non-profit basis. Because German industry, for instance, are rightly so a bit skeptical that they have to pay first for capturing, and then they have to pay the oil companies to transport and to store it. So those are the 3 questions for you, and then I have questions for Barbara, Franziska, and Claude afterwards. Please, Eva.
Yes, the first, how much, I showed some figures of the work we have done with mapping out the potential storage capacity, how much CO2 we estimate can be stored. And what we say is around 80 gigaton, that's 80 billion tons of CO2 can be stored. What we know is that the capacity can be much larger than that, because and that's up to the way we have calculated it. We use it that we just, the calculation we have done is that we inject the CO2 and just up to a certain pressure. So we use the pressure maintenance. We can store the CO2 with producing out the saline water, and that gives a completely different capacity. So with the capacity, I think with the CO2 emission in Europe, I think that can be handled in both offshore Norway and the North Sea basin. I'm not sure we can take all of the world's CO2, which I think the emission is around 35 gigatons, but the capacity is large. So I don't think we should worry about that. I think we shall worry more about getting this on stream and doing it. The other question is, it was a very good question, saying it's related to oil and gas. The reason we can do this calculation and evaluation of safe CO2 storage is due to all the information, all the data, all the competence we have built up through the oil and gas industry. But the CO2 storage will not be related to the oil and gas industry. That's the projects we are working with is related to CO2 emissions from industrial sources, and that's industrial sources that the only way they can reduce emissions is by capturing the CO2, and they need to store it somewhere. If they are not the CO2 they are not being able to use, it has to be stored. So the Norwegian projects is focused on capturing CO2 from industrial sources and permanently stored in geological formation. So it's not related to the oil and gas activity. I hope that was
Thank you.
Yeah, and it was something about the economy. Yeah.
We'll get back to the cost. Thank you very much, Eva. Now, Carrie, you said you had a specific figure as to the capacity of storage compared to the emissions that we have to capture. Would you like to convey that to us?
Thanks, Paul. Yes, I just wanted to mention that if we use the 2019 emission figures from the European Environment Agency, industrial emissions were 587 billion tonnes CO2 equivalent per year. And one of the CO2 GeoNet projects called Geocapacity in 2008 assessed European storage capacity to be at least 116 gigatons. So if we could use only 1/10 of that storage space, we could store 2 decades worth. And it was worth noting that the study done in Geocapacity specifically mentioned that we needed more data to fully assess the storage. So there's even more out there. So we're not worried about capacity. We have the capacity to store. We have the technology to store. CCS is real and ready to go. Thanks.
Excellent. Now, Barbara, over to you, because so far it's pretty easy for us to visualize that the industry will capture the CO2 and they will store it far under the seabed. But your point about using it, it gets a little bit more tricky, because you did use terms such as long-term. You didn't talk about permanence. So if we are, for instance, to use CO2 in plastics, in concrete, in synthetic fuels, tell me about how you see the gains from the CO2 budget here. Is it because we use capture CO2 that we do not use new fossil fuel? Or what is the budget? And many people say, or some people say, the jury is still out on the sustainability part of using CO2 for such sources.
Yes.
Could you talk a little bit about, talk us through this?
Of course. Thanks, Paul, for the question. The sustainability of carbon capture and utilization is still to be debated because, as maybe you remember the circle graph which I showed, there's a huge variety of application options. And this means that for every single process, you really need to assess what the environmental benefits are within life cycle assessment, which is common in the industry. So this to do that is not it's not an uncommon thing. It's just normal to do that. But on the other hand, it means that it's very, very hard to come up with a final statement that CCU technologies are sustainable. You can't really say that. It depends on how it's done. And of course, there's many factors who influence the sustainability potential of each single application, like where does the CO2 come from? Do I need energy? Do I cause emissions when I transport it? Do I actually, where is the product going to? So there's really a lot of questions connected to that, which are obviously also connected to other sustainability technologies. So this is not a feature which is only applies to CCU. But we already have lots of LCAs for very many different applications. And so we know already today that it is possible under certain conditions, which sometimes they need to be favorable. We have a positive environmental balance for some products which are on the market already. This is pretty obvious, like, for example, for the plastics which are produced on the polyols-based polyols from Covestro, for example. So
I have to cut you off there, but I do think we get an understanding that these are technological challenges that you and the industry are very ready to solve. It's just about a matter of experience and scaling. Because I wanted to move to Claude, because Claude gave a very interesting presentation, and to ask her, in terms of the cement industry, now we've heard that we can capture it, we can use it, we can store it, and you gave us some very concrete, concrete double meaning options. But what you didn't say was, you know, what will make you do this? And the question we get in Slido is, do we need public subsidies for this? Is it the carbon price that you need a specific price to get? Or would you like to be regulated? Would you like to say to the government, please demand us to use X amount of CO2 in cement production? What would be your preferred options to reach your goal in time for us?
Thank you, Paul, and that's really an important question. I think I alluded to the fact that we need to make CCUS what we call an investable proposal. There are a lot of policy asks associated with our carbon future roadmap, and I won't have time to go through everything. So I would really encourage everyone, just go on a website and check our roadmap. But what I want to say here to directly answer that specific question, no, it's not dependent on government subsidies, but it's going to be really difficult without the right policy framework and without support to de-risk the technology. We clearly see that we have a lot of pilots. As we heard already, the technology works. We have the technology. We have identified now for our industry around 30 CCUS pilot projects all around the world. But the economic remain challenging, and clearly we need the development of a carbon economy, and that's essential. And indeed, yes, carbon pricing is one of the things that we need to support the development of these technologies. And the second thing that we need is also to support demand for low carbon product. So we also need to encourage customers to also go for the low carbon option. So it's really two angles. I would really say it's kind of push and pull. We need support for the technology, but we also need support for the low carbon products.
Thank you, Claude. I really think that we will need another seminar to look at all those things, because I feel that we come so far in this debate and this technological development. So we really need to figure out what are the triggers that make this happen. But last but not least, Francisca, it was fascinating to see your presentation, because you took us another place and you opened up a whole new understanding of peatland. And I would call it, to me, I got the impression that you were presenting a double-edged sword, something that can bring huge advantage and something that has a fallback. But the questions I received is, first of all, how would you say that peatland areas can be reduced or suffer due to temperature increase because of climate change? And also throwing the question to you about the economics, because obviously we all want to use as much the natural biological system to deal with our problems, but there, as we spoke about with Claude and with Barbara and with Eva, we need regulation, we need financial incentives. What do you need?
Thank you very much. First, about the double-edged sword, I think for peatlands, it's very clear what needs to be done. They need to be wet, and then we have really little risks associated to it, and they have proven that they are a long-term carbon store. So I think that is also a big difference to many other emerging options for, and that's why I also deeply believe that we need to cut fossil emissions. So for the climate change question, peatlands can develop and grow under high temperatures. We have tropical peatlands, so that's not a problem for the peatland. They develop in areas with the water surplus, in landscape depressions along the coast. So temperature is not really the big issue. Probably it's really land use change, conversion, drainage. We may have areas where we have a drop in the groundwater level, where we have less precipitation, but for the majority of the drained peatlands we have, it is not that climate change would prevent us from getting them wet. But we should be fast, because otherwise they contribute to warming. And for the economy, talking about Europe now again, because we are in the European pavilion, the decisive policy is the agricultural policy, the common agricultural policy, because so far we subsidize drainage of peatlands, but we discriminate and do not support wet land use on peatlands. And this is really something that needs to be changed. Otherwise, the common agricultural policy is not at all in line with the Green Deal. And we very much hope that now the strategic plans of the European Union countries will reflect this.
Thank you very much, Francisca. Now, before we end, we have an expert with us who has not given a presentation, which is Aram Kalori, who is you are a climate scientist. And so I would like to here simply throw the ball at you and hear from your perspective in looking at biosphere and atmosphere interactions and greenhouse gases exchange. What is your take on what we have heard? Has this made you more optimistic?
Yeah, thank you, Paul. One thing that I would like to also emphasize from the experience from the Arctic to the tropics, I would definitely emphasize and intensify engagement with the society, with the public, and basically be it their participation in the activities, such as for us is basically now in peatland rewetting, and so they should be engaged more in the research and also in the actions. And for the for all these nature-based solutions, because of the higher acceptability through the public, we can avoid, reduce, and also remove emissions from the atmosphere, and we quickly go from a source to a sink of carbon using all the natural based solutions.
Excellent. I would like now to give the floor back to Carrie as we are ending this session, but thank you everybody for your for your time and the answers that you have given us. Carrie, the floor is yours.
Thank you very much, everybody, for attending this event. I hope that you found something of interest in all of the great presentations and the question and answer session. So I would like to thank everybody for participating. And I see we have a question on women in this topic. And I'd like to say that I'm very pleased to say that we have an excellent representation of the expertise of women in climate change at our event. And I hope we can all move forward together. So we're at the end of our session, and I thank everybody very much for participating. Hope you have a great rest of the day.
Well done.